right. I think we can slowly get started. People are still trickling in, but I think in the interest of time, let's get going. Welcome, everyone. Oops, what's this? Yeah. Good to see everyone here for our invited speaker. I'm really excited to welcome and introduce Gagana Savova. She's an associate professor at the Harvard Medical School and the CHIP program, and she holds degrees in linguistics and computer science, which is I think a very exciting mix and sort of makes the ingredients for a lot of exciting projects that she's been working on over the past years. Before coming to Harvard, she was faculty at the Mayo Clinic, and I think has been in Boston now for 10 years.
Yeah, over 10 years now.
Yeah. And really, I think, without wanting to go into too much detail on what it is that Gagana does, and maybe not to reiterate too much of what she's going to tell us today, it's really if you try to do natural language processing in the biomedical and certainly the clinical domain, you'll be very hard pressed to not use one of her tools, such as cTAKES or data sets, I2B2 and others that she has been working on and annotating. So it's really a lot of resources that make this game easier or even feasible in the first place have been outcomes of Gagana's work. And with that, I'll give the floor to you.
Thank you, Kirsten. So I'm going to stop my video to save some bandwidth, and then I will go back to the video mode for the question and answering session. So as, oops, it's not advancing. Okay, now it's moving. So what I'm going to talk about is a fairly broad landscape of the clinical NLP community and the research. Then I'm going to talk about some data challenges that we all face in the clinical NLP community and that Kirsten alluded to. Then I'm going to talk about some of the research that we are doing in our lab, and that's related to information extraction for cancer surveillance and also treatment information. I'm going to touch upon topics that, although we're doing research, we should not be ignoring, and that's software engineering. And then I'm going to conclude with what I think are the areas that we'll be developing in the next few years. So I'll start with one of our projects and the big vision for that project. And the title of the project is Cancer Deep Phenotyping. So the goal of that project is, given the patient EMR, extract all the phenotypes associated with the patient. And by phenotypes, of course, the focus is on the cancer and the tumors. However, because a cancer diagnosis affects or is linked to the entire patient phenotype, we would want to extract all phenotypical information related to that patient. So here's a small animation of what we attempt to extract. So you're viewing a toy example of an EMR of a given patient. So the patient has, in this case, 5 nodes. The first one is an oncology node. The second one is an MRI. The third one is a pathology node. The fourth one is another oncology node, and then a brain MRI. The highlighted text is the one that is related to the patient phenotype. So we would want to create a system that would actually extract that information, normalize to a predetermined data structure, including mapping to ontologies. And then once we have that information extracted at the document level, the goal is to summarize to a patient level and then deposit into a database for further consumption by researchers or cancer registries. In this case, I'm listing I2B2 database, but it doesn't need to be I2B2. It could be any kind of database that the end user or the developer feels comfortable with. So this is a very broad overview of what we are trying to accomplish. And for the NLPers and the computer scientists in the audience, it probably becomes obvious that this is basically touching every single NLP task that exists, from low-level tasks like sentence segmentation to very high-level tasks, summarization. So how do we go about solving these NLP tasks? Before I touch upon our solutions for that level of information extraction, I'd like to give you a very broad brush summary of the state of the art in the field of clinical NLP. There is this excellent paper by Wu and colleagues. It was published in JAMA actually in 2019, so it's slightly old. Actually, it's quite old in the NLP community. That would be considered fairly old, but it gives an excellent overview of the neural approaches in clinical NLP. The paper presents the state of the art at that point. And at that point, within the clinical NLP community, the neural approaches were being ushered in, along with other representations, like the traditional embeddings, and then using those embeddings either directly in neural networks or within feature-based methods. Since then, since the publication of that paper in 2019, we have had some revolutionary developments in the general NLP field, and that started with BERT, and it introduced the transformer methods for a variety of NLP tasks. So I'm going to briefly talk about the new developments as well. However, some of the review from Wood and al. Still is very valid. The top clinical problems, or the most popular clinical tasks, are still the concept extraction, the phenotyping, and clinical relation extraction. However, there is a very long tail of other tasks, such as information retrieval, natural language generation, disambiguation, translation, which is very important, some forms of shallow parsing, spell correction. So there is a variety of tasks, but the focus is mainly on these three tasks: the concept extraction, the phenotyping, and the clinical relation extraction. And actually, I haven't seen much change in this focus since 2019. The neural approaches are fairly broad, but the paper lists the contributions of the clinical NLP community to the development of the neural approaches. The graph, the figure that you see captures that visually. And the main conclusion from that figure is that there is a lot of effort in creating variants of the state-of-the-art methods, but applied to the clinical domain. That's the fastest growing category. The second fastest growing category is actually taking these variations variants of the state-of-the-art methods and applying them to real clinical tasks. Another fast-growing category is resources, and probably the slowest growing category is developing novel methods. So the community as a whole has been embracing the novel neural approaches, playing with them, but not yet developing completely novel methods for the clinical NLP community. And in my opinion, this makes perfect sense because language is language. We should be thinking of developing generalizable NLP methodologies that are modifiable to a given domain. One other very interesting point of that summary is that 95% of the papers actually do not provide software. And only 55% of the papers give enough details for reproducibility. So I think these are numbers that are quite striking and that definitely need to be changed. But there are many hurdles as to why, for example, software is not made available, probably because the models are not easily released if they're built by using clinical data. However, I don't see any hurdles of why the papers should not give enough detail to reproduce the algorithms. The community is focusing on a variety of languages, and that's table B. English still being the leading language, but there are at least dozens of other languages that are actually being worked on, and that's very exciting. As I mentioned, there are also efforts on the translation of various clinical documents from one language to another language. However, the data sources, regardless of language, about 50% of them are private, institutional proprietary data sets that cannot be shared with the community. So as we know, this is one of the main hurdles within our clinical NLP community. How do we get access to data that can easily be shared with the research community? About 50%, the remaining of the 50% of the data is shared through several channels. One of the channels is the various challenge tasks, and another one is just releasing annotations to the community, and the MIMIC corpus being one of the most popular clinical data sets. So since 2019, as I mentioned, there have been quite a few revolutionary developments in the NLP community. I'm not going to go into detail because all of us know about those developments very well. BERT, BioBERT, Clinical BERT, the T5 models. What I would like to convey through this slide is that we are in the era of the data-hungry methods. Each of these models require billions and billions of words. So if we are thinking of building reusable, portable, and domain agnostic methods for clinical NLP and information extraction, we need a lot of data. So the question is, how do we get the data? All of us are experiencing to various degrees struggles of getting data. And one of the methods or one of the venues to explore to obtain data is through de-identification of the clinical data and then using that data to build models and potentially release the models. So there are two I want to briefly talk about de-identification of the data, some of the challenges for NLP when we work with de-identified data. So it's not that simple, even if you have the data completely de-identified, to actually use the data for building NLP models and doing NLP research. So there are two main paradigms of de-identification of the clinical data. So the first is what I'm showing right now, where you have the clinical text and then the PHI is replaced with some fillers, and those are represented by the bracketed tags in the bottom box. The second conversion is that the PHI, the original PHI, is substituted with realistically looking data. So in this example, the name Mary Phillips is substituted by a realistically looking female name, and in this case, it's Sandy Parkinson. So now this kind of conversion seems much better from an NLP point of view, but as I said, there are some pitfalls in using this kind of data. So what are the main considerations with each type of conversion? Conversion number one, which was the one where you have fillers represented with the square brackets, is that when models are built, probabilities on the fillers are actually learned. And if that model is going to be used, then each incoming document must be run through the same de-identification tool so that you don't have loss of information when the model is applied. However, this kind of de-identification is not suitable for temporally sensitive tasks because the temporal expressions are actually replaced by a filler date. There is also a level of ambiguity as all people names are replaced by one tag and that square bracket name, square bracket. The second conversion, which looks pretty good, again, there's several considerations associated with it. The probabilities are unrealistic but fake fillers. However, consistent name substitution is very hard. One example is, imagine in the original text, you have the following sequence representing the patient name. So you have May Phillips, then you have Miss Phillips, then you have an abbreviation of MP, and then there is a pronoun that actually refers to the patient. These all should be replaced by the same filler, and that's a very hard task. Temporal expression substitution is also very hard. So if the original text says includes a date, but then a season, and then some holiday like around Christmas time, how do you shift all this in a consistent way so that you preserve the temporality of the original text? There is also some ambiguity in the cancer domain. The clock positions are actually used quite frequently. So tumor at 5 o'clock, for example, the temporal expression of 5 o'clock should be disambiguated. Is it a location of the tumor or is it a temporal expression? So in a way, it's the chicken and egg problem. How do we consistently substitute names? For that, we have to have a solution for the very hard task of coreference. The state of the art for coreference for person names is around 0.7 F1. So there will be noise in the data. That's a given. The de-identification, the substitution through the de-identification would not be perfect. There is also noise in the substitution of the temporal expressions. The state of the art for the temporal expression identification trained and used in the same domain, so no domain adaptation, is 0.8 F1. However, if a model is trained in one domain but is used in a different domain, we see degradation for temporal expression identification. So the F1 now falls to 0.59. But then we also need to normalize these temporal expressions so that we know that the same date is substituted with the same de-identified shifted date. State of the art for normalization is around 0.55 F1. I already alluded to the other types of temporal expressions and the ambiguity, especially in the cancer domain. So there are challenges. There will be noise introduced in the de-identified data, yet we need the de-identified data to work on temporality. Hence what I call the chicken and the egg problem. So how do we deal with all these complexities? There is no simple answer at this point. There is this very interesting paper by our colleagues in London, and they explore natural language generation to create more data that then can be used to train models. So they experimented with the MIMIC3 corpus. Their input was the first 10 tokens of the data, plus some structured information. And through a seq-to-seq model, which is an encoder followed by a decoder, they generated fluent text around those prompts. The results are not perfect, but I think it's a very interesting venue to explore, to actually generate realistically looking but fake data in large quantities that can potentially be shared within the clinical NLP community. I'm going to probably skip these slides in the interest of time, but I'm going to just mention that there are some open source tools. MIST is one of them. However, MIST comes with a model that is trained on general domain. So if you want to use it on your clinical data, you must retrain the model. So I emphasize that otherwise it's a very, very good tool. We have used that tool to de-identify data, which then we share through data use agreements, and we distribute the data through the HNLP Center, and then many of the models that are built off that de-identified data are actually distributed in Apache cTAKES. On a positive note, although there is lots of noise in de-identified data, there are some tasks that seem tolerant to that noisy data. One such task is document level classification. So dichotomizing patients into a phenotype such as yes, no for diabetes, the tumor and its characteristics from pathology notes, tumor comparisons from radiology notes, medication signature, radiotherapy treatments, however, not treatment regimens. I want to emphasize that because regimens actually involve temporality. Regimens are the sequencing of the various treatments, so you have to get the sequencing right to summarize at the regimen level. So on that positive note, now I'm going to talk about cancer information extraction, and I'm going to focus on the extraction of 6 core cancer attributes, and that's the DeepPhe project. Some definitions for the non-oncologists in the audience. These attributes are what's called reportable attributes. Each cancer case has to be reported to a central cancer tumor registry, and each case has to be associated with these 6 attributes. So topography is the location of the tumor, and there is a major and a minor site. There is the histology, how abnormal the tumor is. There is the behavior, the tumor growth, and the invasion, whether it's a benign or malignant tumor. The laterality, when there is such associated with the tumor. The grade, which shows how abnormal the tumor cells and tissue look under a microscope. And the TNM stage, which is derived from the T, which is the size of the tumor, the N, the number of lymph nodes, the M, which is whether the tumor has metastasized. In addition to that, all these reportable cancer attributes have to be mapped to the oncology ontology, which is ICD-10. So in the DeepPhe project, we reduced the task to extracting these characteristics for the cancer, and then each cancer is associated with tumors because a cancer can have multiple tumors, and one of them would be a primary tumor, and there could be metastatic tumors as well. Then depending on the type of cancer, there are some specific attributes associated with the tumor. And overall, we extract about 28 cancer and tumor attributes before we summarize to the 6 reportable attributes that are then made available to either the cancer registry or the translational scientists studying a particular cohort. So speaking of data, through our funding from the NCI, we have been collaborating with the UPMC, Vanderbilt University Medical Center, Dana-Farber, Brigham and Women's, also some SEER registries. We have been working with Louisiana Tumor Registry, the Kentucky Cancer Registry, and now very soon with the Massachusetts Cancer Registry. The scope of the types of documents is fairly large. We have pathology, radiology reports, clinical progress notes, discharge summaries, ED encounters, and also we're dealing with some of the CDA, the CDA messaging, the CDA messages that are sent from the hospitals to the cancer registries. As we all know, first we have to develop annotation guidelines for creating the gold annotations, and we have 2 domain experts who actually go through the notes. We track the inter-annotator agreement, and the final agreement is fairly strong, 0.77 to 1, measured as kappa. I always say that because this is such a difficult task that touches almost every single problem within the NLP community, we are using a variety of methods to solve the task. So we are not focusing only on one specific method. So for example, because the neural approaches are the state of the art, we are not focusing on exclusively neural approaches. We are focusing on methods feasible for the specific task. And I'm going to show you some different methods that we have chosen for the particular tasks. Behind the scenes, we have the DeepPhe ontology, and these are some of the characteristics of the DeepPhe ontology. We need the ontology because we have to provide ICD-L codes for all the cancer attributes. So that's the normalization that we do. Here's one example of a branch of the ontology, and that's for ductal breast carcinoma. So you see the class name, you see the class code, you see all kinds of synonyms, and also the source vocabularies. The very bottom, you see the relations between the diagnosis, ductal breast carcinoma, and the anatomical site. So there is a lot of knowledge that is actually embedded in the ontology that we also use through ontology-driven methods. So for the extraction of the core cancer attributes, we have decided to use the classic pipeline approach. Our motivation for using that approach, instead of, let's say, a neural network approach, is that first, the space of the ICD-L, the codes that we have to map, is in the hundreds. To train a neural network that actually does a classification to hundreds of potential codes, you need lots and lots of data. We don't have access to that much data, so we didn't think that it would be feasible to take that approach. Because of that, we are taking, as I mentioned, the classic pipeline approach, where the text is processed through various NLP modules, and then each NLP module implements a different method. So this is a toy example. Imagine that this is a pathology node, so it goes through sentence boundary detection, tokenization, normalization, part of speech tagging, entity recognition, the discovery of the entity properties, relation extraction, summarization at the document level, and the same is done for each incoming node for that patient. And at the very end, we do phenotype summarization. So that's at the super high level how we do information extraction for the core attributes. I'm showing you now the results. These are results as of 3 weeks ago, and they're not published yet. So these are the results for topography for the major site, topography for the subsite, histology, behavior, laterality, and grade. These are the so-called reportable attributes. As you can see, the F1 scores are very good. What I'd like to highlight is that grade is very challenging to actually extract. For various reasons. There is a lot of variability in the language, and also there are lots of abbreviations in how grade is encoded in the clinical notes. So these are very, very good results. And our goal is to actually help cancer registries introduce efficiencies into the extraction and abstraction of cancer characteristics within the central cancer registry system. That central cancer registry system is called the SEER system. And within the SEER, there is a tool called DMS that supports all cancer registries in the country. So the cancer registries are at the state level, Each hospital reports cancer cases to the cancer registries. They send pathology notes, and the cancer registry registrars actually go through the pathology notes and extract the information, the reportable attributes, which is then reported to the central SEER registry. So we are working with Kentucky Cancer Registry to actually implement the DeepPhe system and help the registrars extract the reportable characteristics. So this is the architecture of the SEER DMS system, and then we are inserting DeepPhe CR into the process. So the reason I'm showing you this is because there are lots of software actually decisions that we have to make to implement the tool within a production system. So this is a super high level sketch of the integration of DeepPhe within the Kentucky Cancer Registry system. So now I'm going to switch from the extraction of the core cancer attributes, and which is an illustration of the classic pipeline approach in NLP, to the extraction of the treatment information, which then would lead us into the applications of neural approaches in the clinical NLP domain. So the treatment information involves the extraction of medications, radiotherapy treatments, procedures, and then some level of temporality. So in this case, I'm showing you the timeline of a treatment, starting with definitive therapy, followed by adjuvant therapy, and then the breakdowns of the therapies within regimens. So you see that there are 3 regimens that have been used by this patient. So how do we extract this kind of information from the EMR? What are the challenges for actually doing that? So we have focused on information extraction for radiotherapy. So this is one example sentence that encodes radiotherapy information. The boxes that are highlighted are the various elements associated with radiotherapy. The arrows represent the relations between the radiotherapy elements. So when we look at the template, at the radiotherapy template, we can see that there are about 6 elements represented by each radiotherapy, and then each element is linked to that specific radiotherapy treatment. From an NLP point of view, how could we start thinking about this task? The way we thought about this task is casting the problem first into named entity recognition to discover the radiotherapy elements, and those are the text in the boxes, followed by a relation extraction task, which links then the elements into one treatment. Because there is a limited set of elements, there are 6 of them, and limited set of relations, then we can start thinking about neural networks and classification methods in general, because this classification space is very constrained, unlike the classification space of the core cancer and tumor attributes. So this is exactly what we did, and we have several publications on the topic. So I'm giving you one of the references. And we experimented with two neural approaches, FLAIR, which is character-based, and also BERT, which is token word piece-based transformer approach. The results for the named entity recognition are very strong, and they approximate the inter-annotator agreement, which is given in the second column. So the inter-annotator agreement can be compared to the F1, which is the result in the last column. And you see that there is a very good approximation of the F1 to the inter-annotator agreement. Oops, I'm sorry. For the relation extraction task, we also experimented with FLAIR and BERT, and we used various sizes of the windows around the anchor entities. And the best result was given we achieved the best result using the BERT models within a window of 92 word pieces. And that result on the average is 0.88 F1. Another task within treatment, within regimen and treatment extraction is extraction of the medications and mapping the medications to an ontology. So this is an example sentence, including some medications. We also have to provide mapping to RxNorm. What I'm showing you here is the annotation schema with all attributes for the medication, although at this point, we are not using all attributes to actually build models for, because some of the attributes have very low instances. So we're using some of the attributes, and I'm listing the attributes: strength, duration, form, dosage, and frequency to build the models. So we experimented with support vector machines, which is a feature-rich method, and also neural approaches. The neural approaches was an LSTM. It was pre-BERT non-transformer method. There is a 2-point difference between the feature-rich method support vector machine and the neural approach. Now, we are probably going to release the support vector machine method, and the reason being that the model, it's very difficult to reconstruct any type of text from a feature-based model. While on the other hand, with the neural approaches, because the neural approaches are language model approaches, there is some remote chance to be able to reconstruct potentially text if somebody tries really, really hard. So that's another consideration when thinking about releasing models for broader use by the community. Oops, sorry. Temporality, extremely important but very difficult task. We have been working on temporal relation extraction since 2010, and it's a project that's funded by the National Library of Medicine. It has been continuously funded. We are very fortunate to have that funding. There are two types of relations, of temporal relations. One is called the doc-time rel, and that's the relation of the event to the document creation time. The second type of relation, and we call that rough temporality. The second type of relation are the more finer-grained relations, and those are relations like before, overlap, starts on, ends on, and contains. Contains is the most frequent relation in the clinical notes. So we have found that through the annotations of many clinical notes, and it's by far the one that is represented very, very frequently within the clinical text. The state of the art for the DocTime-rel, which is the rough temporality, is about 0.9 F1, while the state of the art for the finer grained temporal relations is about 0.75. We published last year a paper that uses bird-style multitask learning for temporal relation extraction, and I'm providing the reference, and we just got accepted to present our research on a very novel method for entity masking for training, pre-training and training transformer models. So I don't have the reference for that one yet because it hasn't been published yet, but that will be coming in the NACO, I think in June, NACO conference. So the state of the art, I believe with the latest results, we pushed it to 0.77 for the finer grained temporal relations. However, again, I'd like to emphasize that this is a very difficult task, and it's a difficult task not only computationally, but it's a very difficult task for the humans as well. So I hope I gave you a sense of where we, the NLP, the clinical NLP community are with regards to the state of the art, the methods, and the applications. Now, I'd like to conclude my presentation with some thoughts about where I think we will be going in the next few years. I think one very important line of research is domain adaptation. We have all seen degradations in performance of the models that we build from data in one domain when transferred to a different domain. So for example, if we build a model on cancer data and then use it on, let's say, rheumatology data, we will see significant degradation in the performance. So how can we improve the methods for domain adaptation? Could there be self-supervised or minimally supervised domain adaptation that will only positively affect the performance of the models? Another line of research of great importance is this continued work on transfer learning, and especially pre-training large models of clinical data. I think this is an enormous challenge for the clinical NLP community because the clinical data is actually patient data. So how do we get access to lots and lots of data, potentially from multiple institutions? Then also, how do we get the computational power to build those huge models? So if you remember at the very beginning of my presentation, I talked about BERT and T5, but these are models that are built within huge companies with huge resources like Google. So their computational resources are not comparable to what we have as research labs. So how do we advance the transfer learning framework within the clinical NLP community? I think another very important topic is that we shouldn't get too obsessed with the neural approaches, and that we should think of ways to infuse domain knowledge to guide these neural approaches. So how do we do that? There has been some work on knowledge infusion, but it's in a very nascent state. So how do we push that line of research to guide the data-driven neural approaches? As I said, I don't believe that neural approaches are applicable or feasible for all tasks, because their effects on data size, data quality, language, medical specialty, initialization, hyperparameter selection, and also the enormous computational resources required to build these neural models. I think we need more shared tasks with more data made available to the community. And also, last but not least, I think we have to focus on technologies that address societal problems. And I think we all work in such area, and that's biomedicine. So with that, I finish my presentation, and now I open the floor for Q&A.
Perfect, thank you so much. And especially for the hot off the press results, I think that's always exciting to see the very latest of what's going on in your lab, for example. All right, we have time for questions. And I believe we're using the chat for that. So please type your question in the chat, and I'll read that out. And maybe while you type and order your thoughts, a quick question from me. What's your stance? Where do you see federated learning going? Right. So you presented de-identification as one of the ways of going forward. Right. So make the data less dangerous, I guess, to use in terms of mitigating the risks. Now, can we have everyone keep their own data and still all learn on everyone's data? What do you think?
Yeah, that's an excellent point. Yes. So federated learning, definitely one venue to explore, but that's not without challenges again. So even within the federated learning, we are facing the problems of what data will be shared across the institutions, and can actually each institution build models and share the parameters for those models of their EMR data. And I think there are legal issues that have, unfortunately, that have to be clear before we start exploring sharing data, even in a federated way.
Yeah. And I mean, you alluded, I believe, to that study, right? So to the Google study where they reverse engineered the language models, right, and tried to get input training sentences out of this again, right? So do I read, and you only I thought of implied that you said, oh, you have to spend a lot of effort to get there, right? So do you think it's not really a big danger right now just because it's such a hard to crack nut?
Well, yeah, we're thinking of ways that we can potentially do something like this. Mm-hmm. But again, it's a difficult problem. So we started reading lots of papers on how the neural models can be used for malicious activities and to what extent. So I think we need to have more experiments, and we have to show more results, and we have to potentially convince the institutions that it's not a high risk. It will never be zero risk, but at least that it's a minimal risk to share at least the models.
Yeah, or at least one that's I guess bearable in the balance of the positive consequences, right? Because otherwise there virtually is no health NLP.
Yeah. I know that the tool built at UCSF, he's working with Google, I believe, and they have all the data available to build models. And I asked him, well, can we access the data and can we build models of your data? And he said, no, of course not. It should be behind the firewall. Okay.
Yeah. All right. Anyone else? Do we have any other questions?
I think, is there a question?
Oh yeah. So Laura is asking about, oh no, this is George. Sorry, you guys are typing too fast for me. So George is asking, what's the best approach for dealing with abbreviations? So acronyms and all that. How do we resolve those?
Yeah. So we have been thinking quite a bit about abbreviations, and they pose the problem of word sense disambiguation. So for example, if I remember correctly, MG maps to 7 concepts within the UMLS. So how do we know which is the correct concept given the text? And in the word sense disambiguation community, the state of the art is building models that actually disambiguate the abbreviations. Now with the transformer models, the implication is that the transformer, the model itself, actually learns the disambiguation. So can we, when we have sufficient data, a bird-like model or any other kind of transformer model actually would know how to disambiguate the abbreviations. So potentially using transformer models instead of building explicit classifiers for word sense disambiguation is the way to go.
Interesting. And then as the last question, I think, with respect to time, Laura is asking a very good one, I think, of accuracy. So how accurate and complete are diagnostic codes, so structured ICD codes, CPT codes, and on the other hand, the clinical narrative that's supposedly richer?
Yeah. So we actually, I must say, I have never worked with diagnostic codes or the billing codes. And the reason I have not done that is because I think there are other considerations when a billing code is assigned. So I think there are other policies that are purely not NLP that go beyond natural language processing. And yeah, as I said, on purpose, I have stayed away from billing and generating billing codes.
All right, fantastic. I think we are on time. Gagana, thank you so much. This was really great. And if we have any other questions that people come up with later, I'm going to make sure to route that your way.
Okay, wonderful. Thank you all and enjoy the weekend.
Have a great weekend. Thank you so much. Take care, everyone.
Bye for now.